All right, folks, so we're going to talk a little bit about B vitamins as cofactors. Mostly because the pyruvate dehydrogenase complex has multiple B vitamin cofactors. And now's a good time to kind of introduce this idea or reintroduce it, as we've talked about it a little bit before with some of our different enzymes. But there are multiple different B vitamins that we need to talk about. These three are the most important for the redox part and for the function, but also vitamin B5. Vitamin B1, 2, 3, and 5 are all involved in pyruvate dehydrogenase complex. We talked about vitamin B6. We'll talk more about vitamin B7 and B8 and B12 here as we go. But we should certainly discuss the top four for pyruvate dehydrogenase. So vitamin B1 is thiamine. Thiamine is a molecule that is involved with TPP. And we've talked about what TPP is used for alpha decarboxylations or alpha carbon-carbon cleavages, like in transketolase. Or pyruvate decarboxylase in yeast. So thiamine is used for that. And remember the structure of that guy is this little 5-membered ring. There's more to it, of course, but this is the business end that I want you to know. And remember that that's going to be part of all mechanisms involving TPP. So the pyruvate dehydrogenase enzyme 1 and transketolase have both used this, and the mechanisms are going to be similar. Vitamin B2 is riboflavin, and this is used to make FAD, FADH2. So those two cofactors, well, I guess the oxidized and reduced form of the same cofactor, are used for redox, and these are enzyme bound usually. Okay, so and we're going to see more and more of these. We also will see this with the Flavin Mononucleotide and Flavin Mononucleotide hydride. So the reduced Flavin Mononucleotide. The only difference here is not dinucleotide, now it's just a mononucleotide, but both of these have the same function. We'll see these guys more and more as we get into the electron transport chain. And the structure of this guy is a 3-membered or 3-ring system. It's called the isoalloxazine ring. Okay. Attaches down at this position, okay? And we're able to essentially see this as our FAD. And at these two positions, at the top right here, and oops, oh man, I messed that up. There, that's what it should be. This is FAD, where we don't have any hydrogens on there. And if we were to do the same thing for FADH2, we would see a hydrogen at the top position. Our double bond would swing down between them, and then we'd have one at the bottom position as well. So this would be our FADH2. The same would be true for FMN and FMNH2. The only difference is what that R group is. Okay, so anytime that you see a mechanism with FAD or FMN, we're going to use this. And so riboflavin, Flavin mononucleotide or flavin adenine dinucleotide is right there. So you can remember that. N3 is niacin. And niacin is for NAD, NADH, NADP, NADPH. Those are also redox. Those are soluble. And of course, we've seen these guys before. A lot of times. NAD has been one of our favorite topics so far. This is NAD. And of course, this can go back and forth to form NADH. Okay. NADH or NADPH, depending on what's on that R group. Okay. So niacin is going to be responsible for NAD. So we need this one from enzyme 1. These two are going to be for enzyme 3 of the pyruvate dehydrogenase complex, because remember, it's a FAD first, then NAD. And then enzyme 2 is going to use vitamin B5, which is pantothenic acid, which is used for CoA. And CoA, if you notice, has a SH on the end of it. And that's because it has a cysteine built onto this backbone that's actually only partially a pantothenic acid. I want to just kind of give you show you what the structure looks like. Let me look it up and make sure I'm not going to mess this up. Enzyme A looks like this. I'm going to actually scooch this down here because we're not going to go much deeper onto 6, 7, 8, and 12, but we will talk about them and what they are. All right. Okay, and we got these two methyls. And we got OP, OP. And good old adenine. I wouldn't expect you to draw this, but you should at least recognize what it is and what B vitamin is derived from. Down here we have cysteine. We attach the acetyl here, or whatever acyl group we want. This is important for fatty acid breakdowns. They're going to see fatty acyl CoAs a little bit later here. So we have the essentially made from a cysteine. We also have a essentially a beta alanine situation. Is not an amino acid. This is a beta alanine. And then we have our pantothenic acid, which is this piece. Okay. And so as a big part of that, we need, and then this is ADP. So keep that in mind now. When you get pantothenic acid, what you're actually getting is the beta alanine connected onto this. So the whole thing is vitamin B5. Okay. The cysteine part on the end, we can get rid of that and decarboxylate that. The beta alanine plus this branchy looking guy is all pantothenic acid. And then we have the ADP part on the end of it. So really you only need the central part of the coenzyme A from our B vitamins, right? And these are things, again, a vitamin is defined as something that we get from our diet that we cannot synthesize ourselves. So we need to get this from our diet. And if we don't get this from our diet, we end up with a deficiency, which can cause numerous different kinds of metabolic failure and even death if you have enough of a malnutrition. Okay. We also see the other ones here, cobalamin is vitamin B12. This is an important cofactor for a lot of different groups, specifically like methyltransferases. Folic acid's good for that too. Folic acid is especially important for neural growth because a lot of methylation and transfers happen from folate. So we're going to need that. Also, lots of other things that go on. We also see the other two cofactors that we run into pretty often here are vitamin B6 and 7. Vitamin B7 is biotin. This is used for carboxylase enzymes. We've seen pyruvate carboxylase in gluconeogenesis, which is a biotin enzyme. We'll go into the mechanism of that because we're going to need carboxylases a little bit more as we go. And then finally, we have pyridoxine, which is used for PLP. And that is used predominantly for transaminases and also in glycogen phosphorylase as a non-standard or non-canonical form of PLP. So we have these 8 B vitamins that we have a function, and 4 of these are involved in the pyruvate dehydrogenase complex. Okay. The other 3 or 4 are kind of scattered throughout the body and have different uses. But keep in mind that these have important uses, and I will ask you about them as we get a little bit farther. Okay. So keep in mind that these structures are important, and as we get into the mechanisms next, we're going to need to understand those structures in order to follow along.